Stephen Hawking discovered something so bizarre, so counterintuitive, that the scientific community initially refused to believe it. Black holes, the most destructive objects in the universe, are slowly dying. Welcome to the Cosmos in 5. Today we explore Hawking radiation, one of the most brilliant and controversial predictions in the history of physics. The background: quantum fluctuations. To understand Hawking radiation, we first need to understand something strange about empty space. According to quantum mechanics, a perfect vacuum doesn't really exist. Even in the emptiest region of space, pairs of particles and antiparticles are constantly popping into existence and annihilating each other almost instantly. These are called virtual particle pairs. They borrow energy from the vacuum, exist for a fleeting moment, and then give it back. Normally, this is just background noise of the universe. What happens at the event horizon? Now imagine this quantum froth happening right at the edge of a black hole's event horizon. Sometimes a virtual particle pair forms right at the boundary. One particle falls inside the event horizon into the black hole while its partner escapes into space. Normally, the infalling particle and the escaping particle would immediately annihilate each other. But the event horizon separates them forever. The escaping particle has no partner to annihilate with, so it becomes a real particle and flies away into the universe. But where does the energy for that escaping particle come from? From the black hole itself. To conserve energy, the infalling particle carries negative energy, effectively reducing the black hole's mass slightly. Over astronomical timescales far longer than the current age of the universe for most black holes, this process causes the black hole to gradually lose mass and eventually evaporate entirely. This is Hawking radiation. Stephen Hawking's 1974 paper. Stephen Hawking published this prediction in 1974, and it was genuinely shocking. Before Hawking, the universal assumption was that black holes only ever grew. They absorbed matter and energy but never gave anything back. Hawking showed that when you properly account for quantum mechanics near the event horizon, black holes must radiate. The scientific community resisted at first, but the mathematical argument was so airtight that it was eventually accepted as almost certainly correct. The temperature of Hawking radiation is inversely proportional to the black hole's mass. Smaller black holes radiate hotter and faster. A stellar black hole with the mass of our Sun would have a Hawking temperature of just 60 billionths of a Kelvin, barely above absolute zero. The cosmic microwave background, the leftover radiation from the Big Bang, is far hotter. So, the black hole is actually absorbing more energy from the universe than it emits. It won't start net evaporating until the universe cools significantly. The information paradox reborn. Hawking radiation creates the deepest problem in modern physics. If a black hole slowly evaporates, what happens to all the information about everything that ever fell in? A star, some gas, maybe an entire civilization of aliens, all of it fell past the event horizon. Quantum mechanics says information cannot be destroyed, but Hawking radiation appears to be perfectly random. It carries no information about what the black hole consumed. When the black hole finally evaporates, where does the information go? This is the black hole information paradox, and it remains unsolved. So, here is your thought experiment for today. If every black hole in the universe will eventually evaporate trillions upon trillions of years from now, does that mean every star, every planet, every life form that ever falls into one will ultimately be erased from existence? And if information truly can't be destroyed, where exactly is it hiding?